I think it's time to start this third day about this short-term course on Earth and mass history of Earth and mass extinction. So good morning. And yesterday we have seen the Permian-Triassic mass extinction event. Remember that we have also seen that this was really a huge mass extinction, the largest one, what some people call the mother of mass extinction, if you want. And we will just go on today, and today we will see, in fact, two things. First of all, well, you'll have this on the screen. We'll just go up into the time arrow and see a little bit what happens during the Triassic and the Jurassic. And we will focus on the end-Triassic mass extinction. And you will see that, again, huge volcanic activity is probably responsible for that. And we will start first to have an overview on this Triassic-Jurassic periods. Okay, so after that, I will just, I have a chapter on ocean anoxic event. We already talked quite a lot about that, and I think that it would be quite interesting for you to have a little bit more details. And I will take the examples of the oceanic anoxic event, the global oceanic anoxic event from the Cretaceous. And by this way, we move on again towards younger times. And after that, if we have still some times today, but it's not so sure, we will start to see a little bit the KPG, the end-Cretaceous mass extinction, if we have time. If not, we will do this tomorrow. There is no problem. Okay, so let's go first to this Triassic-Jurassic period. Okay, so when you enter into the Triassic, you enter to, I just say that yesterday, to, if it works or not. Strange, because I plug it this morning. I have a small problem here. Let me see. Maybe I will do something different. Just 1 minute. Okay, sorry for that interruption, but it looks that these things has small problems. Doesn't really matter. Okay, so this is a Mesozoic, and this is a quite long period of time, almost 200 million years. And the Mesozoic is divided in three main periods system: the Triassic, the Jurassic, and the Cretaceous. We have seen that the base of Triassic is age. The age is something like 251 million years, and the boundary between Triassic and Jurassic is something like almost 200 million years. And boundary between the Jurassic and the Cretaceous is around 145 million years, but this has changed a little bit since we get new age dating here. It's a little bit younger, but it's a detail. So you have the Jurassic and after the Cretaceous. Cretaceous, well, the term Jurassic is coming from a mountain chain located in Switzerland. In fact, I am living my house is built on Jurassic limestone, from upper Jurassic limestones. And this is a mountain chain which is located close to the boundary between France and Switzerland. The Cretaceous name is a little bit more complicated because cré in French means chalk. So this is the time of the chalk, okay, Cretaceous. Why? Because especially in the Upper Cretaceous, there is a huge change in the kind of plankton with the incoming of very, very abundant algae like the nanofossils, as you will see. And this accumulation of microalgae, if you want, is giving the choke because this is almost pure carbonate. Clearly, these are very oligotrophic environments. So now we will see in detail. Well, we will see. We will have an overview of the Triassic and Jurassic, and after we will see the end Triassic, the beginning here, with one of the big 5 mass extinctions separating the Triassic from the Jurassic. Here you can see on that picture that Jurassic. Everybody know Jurassic Park, I guess. And, well, this is really the time of these huge, large animals, the dinosaur. Okay, so now, in terms of mass extinction, I just remember you have seen that graphic several times already. But we go up, we are now somewhere here. This is the end-Triassic, and this end-Triassic, as you can see here, again is marked by quite severe mass extinction, a really increase in extinction intensity, and coincide with this central magmatic province, Atlantic province, the CAMP, Central Atlantic Magmatic Province, which is a huge volcanic province, which was really, really large, as you will see. And again, there is not really a coincidence, as you will see. We'll discuss this a little bit more in detail with impact. Again, this impact seems to predate or postdate the mass extinction event, but does not coincide with the mass extinction. And again, there is some sea level fluctuation and also some black shale accumulation. So this extinction corresponds, as you can see here, is quite severe. This is less than the Ordovician, less than the Permian Triassic, almost equal to the end Cretaceous one. But you can see that in terms of genera, this is quite severe, and 76% of species. Amongst them, the conodonts. I remember you that the conodonts are the small jaws of this primitive fish. They are disappearing forever. That means that there is no more conodont after into the Trias, okay? And after some placodonts, these are vertebrate, some gastropods, and the reef are suffering quite a lot. And also I have to add here the ammonite. Okay, so to see a little bit more in details what happened during the Triassic and the Jurassic, we have well, first to go back to what we have seen yesterday. And here you can see that the base of the Triassic correspond to the reappearance of the reef. Okay, I remember you that during the extinction of the Permian Triassic and during so long time, there was no more reef, no more corals at the surface of the ocean during this time. And if you look to the timing, you don't have any more reef, at least during 6 million years. It's probably more. So it means really that you have this very, let's say, stressful condition that I was trying to describe yesterday, meaning that the early Triassic was so warm that all the animals living in low latitude have to escape when they can to higher latitude. That's for sure. The reef cannot move, and so they just die off in everywhere almost. So first reappearance after a lag of at least 5 to 6 million years, which is really long. And after we have clearly a radiation phase, and the next episode is clearly very important. These are the first real mammals, and here these mammals appears close to the top of the Triassic, some 210 million years ago. And here these mammals were first quite small, but they were clearly a very small part of the biota during all the Jurassic and the Cretaceous. But at the end of the Cretaceous, beginning of the Tertiary, with the disappearance of dinosaurs, the mammals became dominant. And by now, clearly, they are very dominant. I remember you that we are part of the mammals. Okay, so on top of that, we have one of the big 5 mass extinction. So this is the end of the Triassic. When I say end of the Triassic, it means that it starts a little bit before the boundary by itself and was going on through the boundary and in the earliest Jurassic. Okay, so afterwards we have a very important episode, as I said. This is the appearance of nanoplankton. Nanoplankton, these are this kind of fragment of microscopic algae which are blooming in the ocean and start to bloom in the ocean in the lower Jurassic. Some people found a few of them in the end of the Triassic, but there is still a discussion about that. Are they really a nanoplankton or not? But the first real calcareous nanoplankton have been found here in the lower Jurassic. But they will become more and more abundant in the upper Jurassic and especially in the Cretaceous. This is important because chalk, after the chalk is the limestone, which is only made by these billions of nanoplankton, will appear at the end of the upper Cretaceous and will cover really large surface, especially in the Northern Europe and in the Tethys, as you will see. So first, calcareous nanoplankton. This is quite important because this clearly will lead to increasing photosynthesis, and there is some change here in the geochemical cycle that we can see, as for example, a little bit less CO2. And after, in the torsion, I will go back to that later on this afternoon when we talk about the anoxic event. We have what we call the first oceanic anoxic event for the Mesozoic, 182 million years ago. And it's a global anoxic condition. But contrary to what we have seen for the Permian-Triassic, for the Devonian, they don't really lead to a huge mass extinction. There is some extinction there, but not so much, okay? So we are at the end of the Lower Jurassic, and if we just go on, we have something which is quite important coming in at the end of the Jurassic, here, somewhere here. This is the first true redists. What are redists? Redists are, I will show you some picture later on. They are bivalve, but they are bivalve which are very particular because they are very, very similar to corals, but they are not corals. Corals belongs to the phylum of the Anthozoa, and the corals are clearly completely different than the redists, which belongs to the phylum of the mollusks. That's to say they have two valves, but they have more or less a morphology which is quite similar to the corals. And well, in paleontology, we call, in evolutive paleontology, we call that this is a convergence morphology phenomena, meaning that if an animal is living in the same condition as the corals and redists, they get the same kind of morphology. I will show you that. But the redists are completely different. They are mollusks. And the redists, later on, during the Cretaceous, they start somewhere in the Upper Jurassic, but later on, they will replace the corals for a while. For a while, because redists got extinct at the end of the Cretaceous, as you will see. The other big event, clearly, this is the appearance of birds. And here, I just show you this very nice missing link, the Archaeopteryx, which is considered as a missing link between the dinosaur and the bird, okay? And that's why, as I said yesterday, part of the dinosaur were surviving to the KT mass extinction, the Cretaceous tertiary mass extinction, without any problem. This is a little bit difficult to explain, but anyway. Well, probably this kind of bird were not very, very, let's say, good for flying. You just probably it looks like to some hens or something like that. But you can see this is quite funny. They have some teeth. They have very strange also members here. And you can see that the preservation here, this is one of the rare fossils, because in the world there is only 10, 12 specimens of Archaeopteryx which has been found. These are very, very rare, and you need really preservation which must be very, very good. But on that fossil you can see all the details here of that animal. So this first bird were appearing somewhere at the Kimmeridgian-Titonian boundary some 151 million years ago. Okay, so this is the first bird. And now, if we look a little bit to that small abstract, small cartoon, you can see here the Triassic. And, well, the early Triassic, this is the time of the recovery, long, very long recovery. For example, for the reef, this was time of extremely hot waters, but gradually you go back to some normal condition. And, well, the corals are reappearing, the diversity of ammonites and the diversity of the swimming reptiles and more developed. We renew a lot of fish species also, and we have again very abundant ferns and seed ferns species among the plants. And well, we have some clearly the first dinosaur are appearing somewhere at the end in the upper Triassic, before the mass extinction of the Triassic-Jurassic boundary. So dinosaur appearing at the end, more or less at the end of the Triassic. And well, it's a new vertebrate group which will dominate after, with this big form, like, for example, this Diplodocus, all these giant sauropods, and you have the birds here. And other things here that you can see also. This is more or less the appearance of large reef, which will dominate, especially during the Jurassic and Cretaceous time. The appearance of this calcareous nanoplankton, microscopic algae if you want, and phytoplankton diversification, plus more or less more and more, let's say, gymnosperm flora. So Jurassic times was, Triassic times was the times of recovery of the biggest mass extinction that we know since more than 5 million years. And the Jurassic time was a time, I would say, of diversification, with some interruption as the one here at the end of the early Jurassic, this anoxic event from the Toarcian time. In terms of paleogeography, the Triassic-Jurassic paleogeography is, in fact, the time of the dispersion of the continent. You have the breakup of the Pangaea, as you can see on this different map here, where the first one, you can see, again see this is the early Carboniferous. And yes, okay, I will go back to the last. Yep. Yeah, I will talk about that later on. Well, I can just answer very quickly here. Well, it means, yes, I will go back to that. I will give you an explanation. When we talk about aragonite seas or calcite seas, it refers to the fact that organisms are preferentially using or precipitating, if you want, calcite during some times, or aragonite during some other times. Aragonite, for example, is part of the shells of a lot of mollusks, like ammonites, gastropods, a lot of bivalves, not all of them, because oysters, for example, are precipitating for the shells the calcite. And well, there is some times during which you have, let's say, more organisms precipitating aragonite than organisms precipitating calcite, and vice versa. And this is mainly due to, well, in what sense, a little bit due to the temperature. When the water is sometimes cooler, the corals, for example, which are precipitating exclusively, at least for the Mesozoic, the aragonite, are less present. But it's mainly a question of ratio between magnesium and calcium. And this ratio is varying because into the calcite, you don't have pure calcite always. There is always a little bit of magnesium going into the composition of a calcite. You have high magnesium calcite, low magnesium calcite. And you have in aragonite, there is almost no magnesium, okay? And this magnesium calcite ratio depends mainly about the magnesium which is coming from the activity to the mid-ridge oceanic. So sometimes, from time to time, when you have time where you have a lot of activity crustal activity, so you create a lot of basalt, you have a lot of alteration, you deliver more magnesium into the sea, and by this way, it means that you favor the precipitation of calcite versus aragonite. So it's a question of that. But there is also a question of the temperature, clearly. Okay.
All these changes all over the globe.
Yes, sure. Yeah. It's global things. But I will show you. I don't have this here, but I can show you this afternoon. Some explanation about that if you want. I can show you a graphics where you can see the time of the aragonite so-called sea and the time of the so-called calcite. Yes? Yes? Yeah, sure. Yeah, well, it's a little bit more complicated because aragonite is not stable through time. And calcite is a lot more stable. So it means that, well, through time, if you bury your sediments, generally aragonite, with time, will be transformed into calcite. And that's why for the paleontologist it's not very good, because corals, for example, if you have an aragonite corals, you have generally it's 100%. You will see if in a modern coral, if you have a modern corals in your hand, you will see all the details, okay? But after a few million years, you bury the sediments, you replace the calcite by the aragonite by the calcite, and all the details of the fossilization are just disappearing. And that's why it's, well, it's a little bit more complicated. Just one see with that. There is, you can have post-diagenetic, post-depositional transformation of the aragonite into calcite. But when I am talking about calcite seas, aragonite seas, I am talking about primary composition of the main organism. But I will show you a curve, a better explanation this afternoon. I have some PPT slide on that problem. Okay, so if I just go back to that, here, Jurassic paleogeography. So this was the paleogeography of the early Carboniferous, and during the Carboniferous and the Permian, you have a collision here, and meaning this is a Hercynian collision, and you get this huge continent at the end of the Permian. This is the Pangaea, and this continent will stay like that during up to the late Triassic. What happens to the late Triassic? Something which is very important, because this is the reason why we have a mass extinction in the latest Triassic. You open here the Central Atlantic. And the opening, it's a rifting, and this opening of the Central Atlantic will lead to huge volcanic activity, namely the CAMP, Central Atlantic Magmatic Province, and this will lead to a breakup of the Pangaea. And during the Jurassic and partly Cretaceous, but mainly Jurassic, you will break this Pangaea, create first the Central Atlantic here, and after you start to open the South Atlantic, and well, it's something which is also important, you start also the drifting of India, which will start is migration towards the Asian plate. And I will show you, can show you that now, in fact, it will be better. I will show you an animation with this plate tectonic. 1 minute. I have just to find it. Why is this thing? Okay, here. So this is, if it works, it's an animation about plate tectonic starting in the earliest Triassic, okay? So this is that. And here, the time, here's the Triassic-Jurassic boundary, some 200 million years ago. And I hope that it works. Yes, it works. So I can comment that. Yes. So you have the time running here, and you can see, no, sorry, I will enlarge this. Oops. Okay. Oops. Okay, so this is starting 200 million years ago. This is the Jurassic. You have the opening here of the Central Atlantic with the camp volcanism. You open the Central Atlantic. This is still late Jurassic, okay? And you open also, enlarge the Tethys. And here you start, India is starting to drift in the early Cretaceous. And you start also to open the South Atlantic here, okay? And India is drifting, as you will see. This is the late Cretaceous, and some in the late Cretaceous, beginning of Tertiary. She will move over an hot spot, sorry. And this is Deccan Traps here. And after, later on, in the late Eocene, Miocene, you have the collision with the Asia, okay, creating the Himalayan mountains. And here you open completely the Atlantic, and while you have some drifting to the north also for Australia, and in the same time, I can show you this again, if you want. Okay, so opening of the Central Atlantic. First, this is here, and after you start here to move a lot of things, Australia, India, and here you start to open first the south of the Atlantic, and after this part of the Central Atlantic. And India is drifting in the late Cretaceous, and you have also a drift, a collision of Africa with Europe. And Africa is going over Europe, creating the Alpine chain. In the meantime, Asia is colliding, India is colliding with Asia, and here you can see the Deccan Traps, okay? And creating this, both Africa and India will create a massive, huge mountain chain, the Alpine chain in Europe, and the Himalaya in India. So this is quite interesting, because I will talk about that this afternoon, but after around 30 million years ago, this will completely change the state of the Earth from a greenhouse condition that we had since a big part of the Jurassic, Cretaceous, and the beginning of the Tertiary, to an ice house that we know actually. And I think that this change in the general cycle is really linked to the surrection, the uplift of the Himalaya and the Alpine chain, which will move, more or less promote the weathering and draw down the CO2 and provoke a cooling, as you will see. Now I can just show you, yes, this animation, why these things, this is especially for the students, why these things are moving. In fact, these things are moving because you have convection here in the Earth, which are provoking this drifting of the plate at the surface. And these things after provoke also some collision. And here what I put, it's a bit fast, sorry. What I put here is this convection movement are responsible of all the plate tectonic, and they are responsible clearly also with this collision. This is an example of the Alps. You can see the African plate going up to onto the European plate and creating the alpine chain. And here, for example, this would be Italy, this would be Switzerland, and the Jura Mountains. And I'm living here, okay, if you want some details about that. So by this way, you create, for example, in Switzerland, some mountain chain. This is Switzerland. My university, I show you that here because he is just here. Lausanne is here, okay? And I'm living here in the Jura Mountains. This is a place where the Jurassic has been defined a long, long time ago. And the Jura is a smooth mountain chain, which is more or less some kind of remaining activity of the Swiss Alps. And this is a view of this kind of fold. And my house is just somewhere down there here. You have a big lake here. This is the Neuchâtel Lake. And this picture is just here, okay? So these are the Jura Mountains, not very high, some 1,500 meters high. And this is here the best known mountains in Switzerland, the Cervin or Matterhorn. This is a ski resort, very well known, even in India, because it's very well known in India. A lot of people are organizing wedding, Indian people, probably rich people, I guess, are organizing wedding close to that mountains. They go just in Switzerland for 1 week, organize a wedding, shoot some pictures, and go back to India. And but well, it's a lot of people are doing that. It's really funny. That's why from time to time in India, I'm very surprised to see some pictures from Switzerland because some people at least know that place quite well. Here, this is just a view. This thing is somewhere here in the central part of the Swiss Alps. And the age here is a little bit more. It's 4,000 and more, in between 4,000 and 5,000 meter high. But the interesting things here, these rocks here belongs to former ocean. They are deeper environment, and they have been overforested by this pile of rocks which are of Africa, meaning that Africa were really going on the European plate. That's why these books is funny books. They just ask a question: these mountains, le Cervin, is it African or not? And it is African. That's why you have giraffe here. But this is a bit of a joke, okay? But this is just to give you a little bit smell of the place where I'm coming, and which is a place where we had, as in India, a huge collision between the African plate and the European plate, giving rise to this big mountain chain. But the Himalaya is by far higher than the Swiss Alps. And now for the fun, I can show you, because you can do model, as I said yesterday, and some people try to do model on what would be the next continental reorganization, the next drifting, the next plate tectonic for the next 200 million years. And this is the result here. You can see we are start from the modern time. Africa is still colliding with Europe. And, well, you can see that we just go back in a future, but not very near future, these are million years, to a situation, to a Triassic, Permian-Triassic situation, okay? Meaning that we'll, apparently, if we follow this modeling, I'm not sure that this is fully correct. I'm going to show you this one more time. Okay. Okay, it's really correct. We are going back to a Permian-Triassic situation. So it means that you can forget the boundaries between lands. A lot of those, and Mr. Trump can build any wall that he wants. You will not avoid this kind of things, okay? So this is this kind of models that you can have. I just speak about that because, well, it takes million years for sure. But actually, and we will discuss this Friday about the Anthropocene, we are coming back not with migration on the plate, but at least climatically speaking, with the climate, to a Cretaceous climate, as I will see you after tomorrow, okay? This is just to give you a little bit taste of what will be the Earth in 200 million years. We have time, you have time. Okay? So now we go back to, if I can, okay, I will just do this paleography. So, well, you have seen the plate moving. Here a little bit more fixed, but this is, we start here with the breakup of the Pangaea, the creation of the Central Atlantic, the South Atlantic, the drifting of India, and the quite opening of the big Tethyan Sea. Okay, so this was the situation when you start from, let's say, the Triassic to the Cretaceous. Okay, a little bit, I just want to move, to spend 5 minutes about dinosaurs, because you will see that the dinosaur didn't survive to the KPG boundary, apart from the birds. And we have a lot of dinosaurs in Switzerland. Tracks. In India, you have a lot of place in the Lametta bed, especially, it's the Upper Cretaceous bed, where you can find very nice, not really tracks, there is some tracks, but not so much, but some bones, clearly, coprolite, and also you can find eggs. And all, for example, the Nagpur area is quite close from here, very, very well known for all the eggs that the Geological Survey, mainly Mojave, has found in the last 40 years. And I just remember a very nice paper of, I think it's Mojave first author, I don't remember exactly, published in Nature, yeah, I think, where they found a nest of eggs. I think it's a Lametta bed. And this nest is a little bit particular because some of the eggs has been broken, and inside one of the eggs you have a snake. And this is a fossil. You have a snake, but the funny things, but not funny for the snakes, that the snakes, the head of the snake is a little bit out of the nest, is completely splashed, okay? Has been broken. So the scenario, it's a very hypothetical scenario, is that, well, the snake was trying to eat, more or less to eat the eggs, which, well, dino eggs, this is a lot of food for a snake. And maybe the big mama dinosaur just come back and splash more this bad guy who was trying to, more or less, to eat the eggs, to rob the eggs, okay? Just to say that in India you have a lot of dinosaurs, but I will show you also after tomorrow that this dinosaur disappeared with the first main phase of the Deccan traps, just a little bit before KPG boundary. So in Switzerland we have also some of the dinosaurs, but we have also some of the oldest dinosaurs. I told you that the dinosaurs were appearing somewhere at the end of the Triassic, and here, this is in the Swiss Alps. You have the mountain chain here, and this is a dam. And if you walk a little bit, you can find very nice tracks here, dino tracks, which has been deposited in a very shallow environment. Why? If you see that picture, you can probably guess why. We can say that is a very shallow environment. These are ripple marks, which are typical for beach, probably, because these ripple marks are symmetrical, so these are links to waves. Okay, so this is very close to the beach. And this is generally the place where you have the best preservation of the dinosaur tracks. The age here, they found quite a lot. The age, they are not so big. As you can see, one is 3 meters. I don't want to meet this guy anyway, but the main one is 3 to 400 kilo. And they were all herbivores, but they were from the Triassic, okay? But in Switzerland, we have also, well, I can show you more or less this guy from the Triassic Dino Park. I can call this like that. They are quite small, quite well preserved, especially a place close to the Jura Mountains where you have some Triassic rocks, sediments, freak. They found this kind of these guys. That's why they put this at the entrance of the town, okay? And, well, there is a lot of these traces. And now if we move to the Jurassic, during the Jurassic, we have also, we have the dinosaur explosion in terms of diversity, proliferation, but also in terms of increasing size and weight. They are really big. They were the biggest animal that had ever on Earth's surface, okay? And here is just to show you on this very nice reconstitution also what was the sea during this time. You have some reptiles here, the ichthyosaur, which are quite well known, some ammonites in a live position. So remember, I told you that they are living in the last chamber here. All this one were empty or infilled with gas and water, which more or less allows locomotion, the fact to go down and up just by adjusting the mass of the water and gas that you have inside the shell, some kind of submarine if you want. And some belemnite here. This is the ancestor of the calamar, which were also very abundant in the Jurassic. And here I show you a place where these fossils of ichthyosaur, for example, this one, and here you have a plesiosaur, which is a marine reptiles, a very nice ammonites. The preservation here is really incredible, and this is linked, the age is torsion, and this is linked to the fact that you have an anoxic event here. If you look to the stone here, the stone is really black, full of organic matter, and meaning that you will preserve everything here. And the ichthyosaur, the preservation is so nice that some of these specimens have embryons inside, okay? So it means that you have really a preservation of the soft part of the body, which is only possible under anoxic condition, because you don't have oxidation of all this part, okay? So there is no decay of organic matter, there is no decay of the bones. Contrary to a dinosaur, if a dinosaur is dying on a beach, clearly after a few years, if it has not been eaten by other animals, all the bones and the soft part will just be oxidized and completely transform into powder of rocks or things like that. So no possibility to have a good preservation. You need this exceptional preservation in order to get these very nice fossils. And there is only a few places where you have that. You have that, for example, where you have the Archaeopteryx, the linking between the dinosaur and the birds. You have that, for example, here. The Burgess Shale in the Cambrian, where you have this Cambrian explosion, also has this kind of things. But here the system, the phenomena for the preservation is not the same. Here you have a preservation because it is anoxic. In the Burgess Shale, where you have all these trilobites and things preserved, this is due to the fact that sometimes you have turbidite, which are covering very quickly the dead body of the animals, preserving these bodies to be completely destroyed, oxidized, and preventing from the decay. So there is different kind in order to preserve fossils for time. Another place, and here we move from the late Triassic to the late Jurassic. This was really the golden time for the dinosaur. This is in the Jura Mountains, and here's the story. I know quite well this place because I worked as more or less, we did a lot of investigation, not about exactly the trace of the dinosaur, but the environmental condition leading to that preservation. And here you can see there is thousands of traces, of tracks. And this has been preserved in some limestone, and you can see here, there, and there is different species clearly. And you know why we found that? Because it was not possible to see them. But well, in Switzerland, when you build an highway, you have first the obligation to investigate in terms of archaeology and paleontology. This is a federal law. You have to investigate 100 meter right, 100 meter left to the highway before to start to build the highway. And well, sometimes the engineers are not very happy with the paleontologist and the archaeologist. They just pray that nothing will be found because it can delay more or less the building for many years, depending on what you find. And here, what they find, it's really nice. They find all these big limestones with a lot of traces, but almost no fossils, no skeleton, no bones, only tracks. Okay, and this place is by now. Some of these traces have been preserved. You can visit them. There is even a museum. And there is quite a large area where in the Jura Mountains, France is here, Switzerland is here, where you can find a lot of this big sauropod. But there is also a smaller one, some theropod with the fingers, okay? And well, in this time, the Jura Mountains were a little bit like that. This is our constitution. And well, you have a lot of traces. And some of them, this is quite interesting, are parallel, meaning that we were migrating, traveling by groups, okay? Not alone. And there is also, interestingly, big traces, parallel, big and small. That means that probably the babies were traveling really in between the groups, okay? So this is clearly interesting to see that they have this instinct to remain grouped when we were more or less moving. So this trace here has been very nicely preserved for one reason. This was a beach, okay, during this time, we know that, and this beach, there was when the sauropod, which is very heavy, was just letting his trace into the mud. Automatically, you have a small thickness of water going into the trace, and here there is some microbial activity. So this is thanks to the microbe that this traces has been preserved. Some small microbial mat which were more or less occupying these traces, and they precipitate calcite, and they preserved the relief of the traces. So this is, I think, very funny to think that these huge sauropods, which the weight is many tons, these are big like an autobus, if you want, like a big truck, were preserved thanks to the most tiny animals that you can find in the surface of the earth, microbes. So I think it's really interesting to think to that, meaning that, well, nature is really incredible. Okay, so for the dinosaur, I said that, well, the birds are coming from the dinosaur, and here, this is just a view of this Archaeopteryx lithographica. Lithographica is name is well, is a little bit easy to understand. Why? because this kind of rocks are made of very flat level that you can cut like that, and that you can use in the Middle Age to make some lithography. This was a way to print the books. Okay? And they were using this stone in some quarry, and that's why they found these 12 specimens of this missing link between the dinosaur and the birds. Okay? The preservation is just incredible. But the size here, sorry, there's no scale. This was very little birds. Like that, no more. And, well, they were probably able to fly, but like a hen, if you want, not not very good in flying, probably. But this is very important because this missing link first is very important for the evolution and has been used by many paleontologists in order to prove that evolution was really the driving force for what we see in the paleontological record. And like this amphibian that I show you, from the fish to the amphibian. And this is clearly very important in order to, this is one of the proof of the evolution theory. Okay, now, before to go into the discussion about mass extinction, just we go on with the story about the sea level fluctuation. Okay, you have seen that, well, during the Permian Triassic, you have one continent, almost very slow activity in the mid-ridge, oceanic mid-ridge, meaning that there is production of the crustal product, like the basalt and so on, is very slow. So, in fact, well, at the third order, sea level is very low. And you start to increase the sea level during the Jurassic with a maximum here during the Cretaceous. This maximum corresponds to a black shale accumulation again. We'll go into details about that this afternoon. And clearly this is linked to the breakup of the Pangaea, which happened here. And you have more and more volcanic, submarine volcanic activity, more and more, let's say, creation of oceanic crust. So more and more the volume which is available for the water is becoming very small. So clearly the water has to go somewhere and go up into the continent. Okay, so this is expansion of this is clearly a huge transgression. And this transgression is maximum here. And after, you will get a regression, which is mainly linked to cooling and the presence of ice caps, as you will see later. So I already show you that, which is this sum up of different parameters. But just to show you the global climate, now you are a little bit more familiar with that. I guess that these things now must work. Okay, so okay, come on. Bizarre. No. Okay, I have it. Okay, so you have this global climate change. Now you can more or less, we are somewhere here. We have seen all this, the beginning of the origin of life. Now the Cambrian with some, let's say, quite hot climate. The glaciation of the Gondwana, the Carboniferous Gondwana. And you can see that when you enter into the Jurassic Cretaceous, again, you enter to a greenhouse condition. And you, from there, from the base of, let's say, a little bit after the Cretaceous tertiary boundary, you go into, again, some icehouse age. Sea level, as I said, mainly huge transgression in the Cambrian up to the Silurian, and from the Devonian to the Trias regression. And again, we start to transgress with a maximum which is located here in the upper Cretaceous. And again, a decrease of sea level in the Tertiary. CO2 content, well, there was a lot of CO2 here because oxygenation was not complete here. And after, clearly, you have a drop in CO2. Why? Because you have this huge forest from the Gondwana. This is a Carboniferous. But you can see that again in the Cretaceous, we have quite a lot of CO2. And we are here actually a little bit higher. So be a bit careful. Yeah, clearly during the Cretaceous, there was more CO2 than now, a lot more. But the speed, the acceleration is not the same. We are producing a CO2 at a speed rate which is not comparable to any change that you can see here. And you will see that if we just going on with the quantity of the CO2 that we are releasing, we humans are releasing, we will be quite soon back to the Cretaceous, okay? And this is what I was saying about the plate tectonic. Here's the supercontinent breakup. Again, the Pangea supercontinent during the Triassic, Permian Triassic, and the breakup corresponding to the Jurassic Cretaceous. And clearly these two times, especially that one, is marked by a lot of volcanic activity. Okay, so now let's go a little bit in more details about this mass extinction event that we had at the end of the Triassic. I will not give you really a huge presentation about that because, well, a week is quite short at the end. But anyway, here this is this mass extinction. You have here the date, which is, well, 201 more or less, well, let's say 200 million years ago. And you have here some reptiles like the placodont, but conodonts. These are these small, primitive, let's say, chordate, maybe fish, are totally disappearing. There is no more conodont after this time. And you have a huge extinction among the bivalve, ammonoids, plesiosaur, ichthyosaur, which are these marine reptiles, some therapsid, which are, well, vertebrate, and amphibian. But the numbers here are quite high, we can say that, but clearly not comparable to the Permian-Triassic mass extinction, okay? And here, on these things, this constructor, this is in French, but these are build-up, if you want. So these are the organisms which are using mainly calcium carbonate, mainly because there is sponge with silica here, using carbonate in order to make your shells or to make the corals and so on. And you can see that this time corresponds to a huge calcification crisis. How do you promote a calcification crisis? Well, it's mainly by the fact that you are lowering the pH of the global ocean. How do you lower a pH of the global ocean? This is generally mainly due to the fact that you have more CO2 into the atmosphere, so you will lower the pH by this way. Okay. One thing also which is quite known by the paleontologists, this was a time where almost all the ammonites got extinct. Almost all except one. So we can say that for ammonites, well, this crisis was quite big. And you can see here the pattern of extinction. Oh, this thing is not working very well. Okay. The pattern of extinction here of the ammonites. This is the last stage of the Triassic here, and the first stage of the Jurassic. And you can see that only one, let's say, family is going up, is surviving. This is a Psiloceras. And all the other one are just dying, which is quite, let's say, impressive. But why? It's a bit difficult to say. It's probably, again, a calcification crisis, because ammonites, you know, the shell of the ammonites is, at the beginning, aragonetic, and maybe these animals have some difficulty to more or less precipitate calcite in with a pH which was a little bit lower. It's a maybe, but one thing is quite sure also is that reef organisms are suffering also quite a lot. You can see here that there is really a strong decrease in diversity of the corals, for example, but also some calci sponge and so on. So this is clearly a problem of acidification of the ocean, and we will see this in more details after, maybe why. I will show you a cartoon about that. Okay, if I just go. Okay, on land, well, this was also, as I said at the very, very beginning during my introduction, sometimes very difficult to really evaluate the more or less intensity of an extinction on land, due to the fact that, for example, well, for the dinosaur, the bones and skeleton are very difficult to find, and you cannot do taxonomy based on dinosaur tracks. It's impossible. So that's why sometimes, well, it's not so easy. But anyway, what we can see here is that, well, there is quite an extension here. You have the marine reptiles maybe here, namely the amphibian, the dinosaur. You can see that at least for the amphibians, which was quite a hard time, but quite a lot of dinosaurs were surviving, and after the diversification of dinosaurs, especially in the middle Upper Jurassic, was quite fast. So difficult to say about the extinction on the continents for this time. Okay, so, well, we already talked about that. Just to show you a little bit in more detail, a paleographic map. This map are the Scottish map, the one that you can find on ResearchGate. This is at no cost. You can upload that. There is no problem. And Scottish is very kind because, well, you can publish, you can use in publication this map. You just have to say this has been gently provided by Scottish. Some of the people are selling that. So, but this one, you can use these maps. There is strictly no problem. And here you can see, well, this is early Triassic. We already discussed about that. And here just early Jurassic. And what I want to point out here is mainly that the central Atlantic here is starting to open. There is a rifting here. So interestingly, you can understand that this rifting concerns part of Africa, South America, and USA, North America, let's say. And you will find basalt as well as in New York State than in Morocco, for example, or South America. You have still quite a big Pacific Ocean, but the Tethys Ocean is developing quite a lot, especially in Europe. You can see Switzerland would be somewhere here, okay? And India, well, is still, for the moment, attached to the Gondwana. And this is an overview of this Pangea breakup, more tectonic maps, if you want. This is done by Stempfli. Again, this is not on ResearchGate, but Stempfli was a professor at the University of Lausanne. But here's the interesting things. You can see the starting point of the rifting here of the Central Atlantic, which will trigger the magmatic activity leading to the camp volcanic activity. So this is quite interesting to see that. And here, just a view in two places. Well, clearly at this time, New York, which was somewhere here, was very close from Africa, very close. There was no Atlantic here separating the two continents. But you can see here, this is all the basalts and the dikes crossing a lot of sediments, which are sometimes very rich in evaporites or in coal, which may lead to a lot of sulfur dioxide and a lot of CO2, which will enrich more or less the magma and go into the atmosphere. And this intense volcanics can be clearly seen here along the Hudson in the New York states. These are very nice basalt, which form a real palisade, as you can see here. This is National Park in US. And here I show you some place in Morocco where I am generally doing a lot of field trip with students. We are mapping in some place. This is a place where also we have found some dinosaur tracks, as I showed you at the beginning. And here on, well, Morocco is here. And the place that we are looking at is this place. And you see here a dike, which is linked to this rifting, okay? And this rifting is just huge, as you can see. And this promotes more or less some giant dike. And this one is really incredible. It's a dike, more or less the length of these dikes, which is made of, let's say, dolerite and with some basalt. Here's some kind of more than 200 kilometers long and crossing all the anti-Atlas. This is a mountain chain here, which is somewhere located here. And you can, and here this pictures is taken here. You can see here that, well, I say 200 kilometers, 400 kilometers is not really proved, but at least what you have on the map here represents 200 kilometers. And this is a wall. And the thickness is 100 meters, and well, the length is incredible. But also in Morocco, and this is, for example, that place here, you have basaltic traps, a little bit like in Deccan, which are more or less covering red bed, continental red beds from the Triassic here. The thickness of these things is not so huge as for the Deccan, but you have to think that if the thickness was not so huge, the superficie of this volcanism was just incredible, very probably. And this kind of dikes are crossing all the Paleozoic pile of sediments, and some in some parts this Paleozoic pile is very, very enriched, for example, in organic matter, which will lead to more CO2 into the atmosphere. So again, you have seen that several times, so I don't want to really spend too much time on that. Again, a nice correlation. Here on this quartile things, we are somewhere here. Okay, this is the Triassic, and a good correlation. So, in fact, for that, this is a new illustration from Percival, published in Earth and Planetary Science, which show really the very nice temporal correlation of these large igneous provinces with here oceanic anoxic event and extinction events. Okay, and here you have, for example, the Ordovician, the End-Devonian, the End-Permian, and Guadalupian, and we are here, okay, to the End-Triassic. So we still have to go there, okay? This is what we will do during the next 2 days and this afternoon. We will see the anoxic events, which are linked also to volcanism, but we will see clearly for longer time the end Cretaceous mass extinction. Okay? Okay, so, well, you by now you know quite well this kind of cascade, let's say, of events that are more or less made of feedback, which will, for example, accelerate warming. Well, here, this situation is quite simple. You have this breakup of the Pangaea, a huge volcanic activity, huge emission of CO2, some warming, you increase the weathering, you increase the productivity, and you get the anoxia. On the longer term, you will sequestrate the carbon and get a cooling at the beginning of the Jurassic. This is not very well known. But these things lead probably to the extinction. And here, there is some question mark still, but the scenario is, to me, quite clear. What about the impact? Well, because we didn't speak too much about impact, but be quiet, we will speak a little bit more about impact for the end Cretaceous event. I will explain to you why we think that you have impact or not. And there is some impact close to the, let's say, Triassic-Jurassic, thank you, to Triassic-Jurassic boundary. But none of them coincide really with the extinction. And a very nice one is, this is a view from the sky to the Manicouagan crater in Canada. 70 kilometers in diameter, so this is quite big, but this is too old. This is in the late, this predates the extinction by probably a few million years. So it's nothing to do with mass extinction, and the diameter of the crater is probably too small to be really, let's say, detrimental to the biosphere. But anyway, there is some multiple impact close to the end of the Cretaceous Tertiary. You have some crater here, but if you look more or less to all this crater, Rochoir, this is in France, for example, they are quite small. But it may be possible that 1 million years ago, before the Triassic-Jurassic mass extinction, there was some kind of meteorite shower coming onto the Earth, which may had maybe an early stress on the biosphere. This is not impossible, but clearly there is no crater which will really coinciding with the mass extinction, and these craters are quite small. The bigger one, Manicouagan, is 70 kilometers one, but all the other ones are more or less in the order of 15, 25 kilometers in diameter. That's to say almost nothing. So we can forget this idea about connection of big impact and this mass extinction event. And there is no iridium at the boundary. So iridium, it's an element of the group of the platinum, which is known to mark the impact of a meteorite on Earth. I will go back to that when we'll discuss detail the Cretaceous Tertiary boundary. So this is a sum up here for the continental and the marine groups. You have here more or less so some of them, but you can see clearly that, well, there is some extinction on the continent, but mainly it concerns ammonites and the reef, coinciding for huge volcanics, and it seems that all these impact crater here, you can see, are predating for a few millions and more than few millions years this mass extinction event. So there is no way really to correlate this impact with the mass extinction. And to finish, this is just a small sum up, which has been published by some people, also paleontologists from Lausanne, Jean Gay. And this is a quite sum up of what you can see here. But it shows also some, let's say, discrepancy in the scenario. This is all not all very well known, I have to say. There is a few problems still. But anyway, you have here the Triassic-Jurassic boundary, and the mass extinction event is occurring here, and this mass extinction event is marked by negative peak in delta C13, which seems to correspond to the onset of the camp activity, the volcanic activity. And here, this is clearly a biocalcification crisis with the extinction of corals, ammonites, calcareous now fossils, and so on. And after, well, this cooling, I don't believe it too much, maybe. It may be due to the fact that at the beginning, the first intrusion of volcanic is crossing the sediments and maybe deal with a lot of sulfur and will more or less release a lot of sulfur dioxide into the atmosphere, leading to a small cooling. But the overall things would be, I guess, a greenhouse. And by this greenhouse, you create, by increasing nutrient and so on, some anoxic condition. And the reappearance of coral reef in mid-high latitude is occurring quite later. It's not the same intensity as for the Permian-Triassic mass extinction, but still you have to wait sometimes in order to get again some coral reef and to get ammonite diversification. The problems here, and here's a little bit a problem to me, but it looks that we still more work on that things. But you can see here that the main, more or less, crisis correspond evidently to some volcanic activity, but the main volcanic activity seems to be located in the lowermost Jurassic. Why? I still don't know, but it could be also that the dating here is not very good still. And people have to probably date better these things, but unfortunately for the Camp province, this is not like the Deccan, where you have a lot of zircons is a red ball. Here there's not so many red balls, and the zircons that you can find generally are linked to dikes which are predating the volcanic activity. So sometimes not so easy. And here I think that these people has to work a little bit much about this dating. And anoxic condition also is a characteristic of the lowermost Jurassic, which may explain also the delay in the recovery. Okay, so I have finished for this part. So we can now move to the next one. If you are still surviving, it's okay. For, let's say, no more than half an hour. And so let me just... So I decided to talk a little bit this afternoon about this afternoon and not later, as I was thinking, about the anoxic event, the global anoxic event, because you have seen that in all this extinction, apart from the Cretaceous tertiary boundary, but here we have an explanation for that, very probably. You have black shell occurring. This is typical episodes of a mass extinction event. We have seen that for the end Devonian, we have seen that in part for the end Ordovician, a lot for the Permian Triassic, where probably the global ocean was completely anoxic, and sometimes euxinic. That's to say that the anoxy was reaching the surface. And well, we have also some black shell at the end Triassic mass extinction. So this is clearly something which is occurring for all apart one mass extinction. So I think it would be interesting to see that in more details, and also because well, by this way, I will talk essentially about anoxic event of the Cretaceous. We can move toward the actual time, and we can follow more or less the arrow of time. So let's introduce that. for, let's say, 20 minutes. Okay, so first of all, here you have a very nice picture. A very nice picture of a place where you have a huge accumulation of black shale. You can see that this cliff here are completely black, and the age is Cenomanian-Turonian. This is the period where the sea was at the highest sea level, and all these cliffs are located close to Mauritania. You go to the south of Morocco along the Atlantic coast. And here I think it's quite interesting to see, and this is a good illustration of what Lyot said about well, the past is the present, or the present is the past in geology, this uniformitarianism theory, meaning that, well, we really need to go to the present and backward to the past in order to understand the geological phenomena. Here it's funny because, well, this cliff has 93 million years old, okay, Cenomanian-Turonian, full of black matter, of organic matter. This is a place where people are drilling quite a lot, especially offshore for petroleum exploration. And this actual sea here, this is the western coast of Africa, is one of the places where the upwelling are very active and where anoxic conditions are also prevailing along the slope. So it means that, if I can say that, in 93 million years, nothing has changed on the western coast of Africa. This is always under anoxic condition. Okay, so what happens during the Cretaceous? We have this since the Jurassic, and now let's have a look for a few minutes about the Cretaceous period. I say at the beginning that Cretaceous mean in French Crétacé. In German, it's not very nice, it's Kreide. And Cretaceous means cré. This is a chalk in English, cré in French. And the chalk is made of billions of tons of these microscopic remains of algae, the nanofossils, okay, which are typically carbonate builders. And they are blooming really during the Cretaceous like crazy. Meaning that, you can see the duration. It's quite a long period. And there is one important thing occurring in the Valanginian. Why Valanginian? Because, it's coming from a name, Valangin, and I am very proud of that because, here at my place, close to Neuchâtel, to the GIAN Mountains, where I am living, you have a small village, the name is Valangin, and another small village, the name is Haute-Rive. And these two international names are coming from that place, which are located around 15 kilometers from my home. And during my PhD thesis, I was studying more or less the Berriasian, Valanginian, Haute-Rivian interval from Switzerland to south of France. And I started to work first close to the Valangin village and Haute-Rive village, where the historical stratotype has been defined. Why? Because in Switzerland, the first Academy of Geology has been founded in Neuchâtel, but not by Swiss people, by German people, because Neuchâtel was part of Germany. It's a complicated story for a while, okay, before to become Swiss. So that's why, well, in this academy there was some geologists, and at this time there was not so many ways just to move through the GIAN Mountains, so they chose more or less to study the layer, the rocks which were very close from the university. The university is very close from these two villages, Valangin and Haute-Rive. And here, the first angiosperm flower plants, this is quite important, are just appearing during the Valanginian. Explosion of this angiosperm will be a little bit later, especially into the Albian, as you will see, Aptian Albian and Cenomanian. But this is very important things. And after, is what we will see this afternoon. We have several anoxic events here, repetitive one. And you can see we have 1, 2, 3, 4, and maybe after 5, because we have to take that one, and so on. In between, we have more or less a time during in the base, at the base of the uppermost Cretaceous, when rudists are replacing corals. I will show you what is a rudist just later on. Rudists have this bivalve, which are colonial, and making some kind of reef like the corals are doing. Okay, and after, on top of that, and we will see later on, maybe starting this afternoon, not sure if we have time. This is a KPG extinction with a dinosaur ammonite, rudist extinction, and so on. This is one which is linked to the Deccan traps and the meteorite. Okay, so now there is also something which is quite important here. Plates are moving, plates are colliding, and you have an orogeny, which is a Laramide orogeny. Especially, it's a question. It's very important for US, Central America, and partly South America. And this is important because these things will reorganize the plate, especially during the Campanian maestration, which are the two last stage that you have here. Okay, Campanian maestration. And during this time, this reorganization of the plate tectonic will create new straits and new current and create some kind of cooling. And we'll get, for the first time, probably, surely of the Cretaceous, some ice caps at the Campanian maestration boundary, which is quite important because this will induce a stress well before the KPG boundary, which have to be added to the story of the mass extinction. Okay, so just a very short view of what happened in the Cretaceous. You have here some kind of more or less marine diversity among the vertebrates, and the very important increase in calcareous nanoplankton, as I said, and also in foraminifera and diatoms. Diatoms are, let's say, fruit, if you want, of algae, but the particularity of diatoms that they are precipitating silica. They are not carbonate. And diatoms, you can find it in marine environments, but also in lakes. In Indian lakes, for example, there is quite a lot of diatoms because silica is available if you weather, for example, the Deccan traps. And the lake, because I worked quite a lot in a project around Nagpur, we had two students, master students from Switzerland came here, took some course from 2 lakes from Nagpur in order to more or less, we will discuss this during the Anthropocene discussion. I can explain a little bit what we have done in India, maybe even show you a little bit what we are doing. We are trying to more or less trace the story of the last 400 years of these lakes. Maybe less because these lakes are generally linked to dam which has been built up by the English. So they are quite recent sometimes. But we are using also more or less a very nice correlative tool that you will discuss. We will discuss during the Anthropocene. This is the cesium anomalies. And in India, you will see that cesium anomalies are numerous. You know why? From where is coming the cesium? It's a radionuclide from the atomic bombing attempts, okay? So Generally, what you get is a huge peak in 64. I will explain that later on, and a huge one in 86, 7. This is a Chernobyl one in Europe. But here we were very amazed by the quantity of peaks that you have. And this is coming clearly from the competition between India, Pakistan, and China. So stratigraphy of this kind of geochemical markers was not so easy, I can tell you, because nobody wants to tell you exactly when it happens, for sure. So let's see, but we can discuss this later on. But anyway, let's go back to that. And while we have here also, while huge dinosaurs are clearly well developed in all the Cretaceous, they start to decline somewhere 5-6 million before the Kitty boundary, links probably to this cooling. And you have this very huge mass extinction which concerns the rudist, but rudist reef are declining earlier. Ammonites and other mollusks, calcareous nanoplankton, planktonic foraminifera, dinosaur, and so on. And the most important things, this is also the development, the radiation of the flowering plants, the angiosperm, which starts somewhere here in the Valanginian, but were very, very abundant in the uppermost Cretaceous, and which correspond to a decrease in gymnosperm abundances. Okay, so just to show you here also something which is quite important. This is the sea level fall and rise, but mainly sea level was very high, and especially at the Sumanian-Turonian, this is a record. Sea level at the Sumanian-Turonian boundary was 80 meters higher than the actual sea level, which is quite a lot. And clearly, the important things here during more or less the Cretaceous, this is the appearance and the dispersion, the proliferation of the flowering plants, the angiosperm. That you have these events here coming from the seed forms and dominating after the vegetation has actually, okay? Angiosperm are very important in the way that you can more or less these plants can migrate, because they are clearly not using only the help of the wind, but also the help of the insect by pollination, and this is quite important. A few words here about the planktonic life. It's a very small organism. Here I just show you, well, the chalk. This is in England. All these cliffs are very, very white. It's almost 900% of carbonate, which are made by billions of tons of very small disc, which belongs to some microscopic algae, which were proliferating during this time, especially in the upper Cretaceous. And in England, in the North Sea, in Denmark, all this chalk, more or less, for the upper Cretaceous. This is phytoplankton, so they are plants, if you want, algae, remain. And here I present you the evolution of some planktonic foraminifera, which are not very big. These things is a question of 10 microns, something like that. And these things a question of maybe 150, 200 microns. So this is more or less the good things here. It's that the diversity is huge, like these ones, and you create very, very quickly new species. So more or less it means that the renewing of the species is a very good thing in biostratigraphy, because you can refine the biostratigraphy, because you have a number of species which is really big. And these are planktic foraminifera, so meaning they are not benthic, they are not living on the seafloor, but they are living in at the surface and deeper ocean, depending a little bit of the species. I just remember you that in the ocean there is a limitation to the carbonate precipitation, which is quite important. Is your ocean where you have this calcite or carbonate compensation depth, lysocline, which vary through time, but at 2, 3, 4 kilometers, depend from different factors. There is a line where you dissolved all the carbonate. So that's why at a very deep location, like the mid-ocean ridge, you have only radiolarian, which are precipitating silica, but you don't see any carbonate. Radiolarite are very deep sediments, which are made of radiolarian, which are only consist only of silica. And all this guy will be dissolved, okay? This is quite important. And there was some period where this lysocline, which normally is located between 2.8, 3.8 kilometers down, depending a little bit of the condition, were more or less shallowing up close to the surface. And this was probably the case. We'll show you this Friday for the PTM, Paleocenocentemal maximum, where the conditions were such that the CCD, let's say the compensation depth for the carbonate, was very close to the surface, very probably. Okay, so these are really for the plankton, okay? Now, the benthic, well, it's always the same kind of animals, but compared to the Paleozoic, there is a lot less brachiopods, but a lot more mollusk, and especially this new organism, which were appearing, if you remember, in the upper Jurassic, and were very, very abundant, especially in the upper Cretaceous. These are the rudists. And these rudists are, this is in French, but replacing the corals during this Cretaceous. This is what we are in. I just add this flu slide. They are not in your the copies that you have. But this is a reef, and you can see that they are very similar to a coral, in fact. If these things want to work, okay. You can see here, this is a bivalve. You have a big valve here, shell, and another valve which is just closing on top here. And by clapping, this animals is filtering, opening slightly this upper valve here. And they are forming, during the upper Cretaceous, reef, and replacing almost, corals were still there, but almost the corals, okay. And they are really big. This could reach more than 1 meter in length here, okay. And they were very, very, very successful during the upper and uppermost Cretaceous, but they disappeared at the KT boundary. So now, in terms of sea level, well, sea level, as I said, is during Cretaceous mostly very high, with a maximum here, which has been probably attained here. And this sea level here is increasing and start to decrease in the uppermost Cretaceous. And you can see here that, well, the Cretaceous paleogeography is marked by a very large transgression, which is first linked to a central Atlantic opening, the Tethys expansion, a lot of crystal production, as you will see this afternoon. And, after you open the South Atlantic and you start the drifting of India towards Asia. And, this is here the situation in the late Cretaceous. Africa is drifting against Europe. India is continuing to drift and will form and will more or less pass over hotspot and create the Deccan traps. And this is in the tertiary, just to show you more or less the resulting things. In the tertiary, you have the Africa-Europa coalition, with the formation of the Alpine chain, and the India-Asia collision with the formation of the Himalaya. Okay, so I will finish here, and we will start at 15 past 2, 1 hour, okay, in 1 hour. Thank you very much. So just to say, some of the slides are not in your books, some of them, but just a few of them that I just had this week, thinking that it was probably important that you get it in order to understand better what I am talking about.